Hello and welcome to this video describing how Window to the Stars works. This is video number 2 in the series, and as you can see from the plot that I'm showing here, we've already had an introductory video where we've made our basic Hertzsprung-Russell diagram. I very much urge you to go read that before you come back to this one. Okay, so we've made a Hertzsprung-Russell diagram, but what else can we say about this star? Well, we have a number of tabs up here which are extremely useful in exploring the structure of the star. So let's start by going to this tab here. What's the Rho T tab it's called. Why is it called Rho T? Well, Rho is the symbol often used to describe density in a star or indeed in anything. And so what this shows is the central density on the x-axis. It's the logarithm of that. Remember before we said logarithms are such that 2 means 100, 3 is 1,000, and so on. So in this case, you see the star starts its life down here in the bottom left, and a central density of around 200, just under 200. But it has a central temperature just under, or just over 10 to the 7 Kelvin, which is 10 million Kelvin. That's hot. That's really hot. So the center of the sun is born when the nuclear burning kicks off. It is extremely hot. And as the star ages, it moves off to the right here. And we can see that by labeling with the time. There we go. We see 10 to the 5 years here, 10 to the 9 years here, and so on as we go up here. Turn those off for now. So you see the star ages from left to right. And this particular model gets hotter and hotter and denser and denser. And you see at here is where we cross this dashed line. And that dashed line, according to the key here, is the helium burning line. That's where helium ignites. So at this point, the star ignites its helium and it zooms off to a different trajectory. In fact, the code stops at that point because the numerics are very difficult. But that's fine. We've done all the hydrogen burning, which is 90% of the life of this star. So the star zooms off to the left. You'll see there it's 10 to the 4 times more dense in the core. It's 10,000 times more dense than it started. It's heated up by a factor of nearly 10 as well, going from 7 down here to 8 up here. But you can see that certainly the density is the thing that's increased most. So that's what you can look at with this diagram. You can use, for example, the middle mouse button, in this case, to zoom out. And if you click the middle mouse, you can zoom around as well. Remember, we can select squares like this. I can zoom back out using the arrows up here. If you zoom right out, you can see there are multiple lines. These are the different burning phases for the star. So, for example, to burn carbon, you'd have to cross this green line. Now, the sun doesn't get there, at least not yet. The oxygen burning is this blue one. It certainly doesn't get there. There are other lines up here. These are the instability lines. For example, the electron captures in the core should happen if you're hotter than this green line, or sort of greeny yellow line here. The sun never gets there. The sun's actually quite a boring star in terms of nuclear synthesis, but it's a good thing for us being alive on Earth. Otherwise, it would never have ever got this far. Now we can also click on the Structure tab. This allows us to plot things such as here, for example. This is the x-axis column. If I want to plot time on the x-axis, I click on there, then I click here, and I can plot it either linearly or in log, or the logarithm of the modulus. That means the log of positive numbers. Or I can take 10 to the power of it if I want to. But let's just plot it linearly for now, which is a typical graph that you're used to. And let's say I want to look at the radius as a function of time. Well, I click on that and I click here linear. I want the linear radius, but it's actually log of radius because that's what it says on the left here. It says log radius as a function of time. And there you see the logarithm of the radius. Remember, 0 is 1 solar radii, 1 solar radius, get my Latin right. And you see that's roughly what, at 5 billion years, that's roughly what our star is, which is supposed to be like our sun. You see at the end of its life, it shoots up. This is when it becomes a red giant. You can also plot 10 to the power of this. That's the opposite of a logarithm. So if we do that, wait a couple of seconds and it plots. There you go. Now you see the reason we use the logarithm is that if you do this, you see nothing down here. It's just always down near 0. It's actually around 1, but it's near 0. But then it spikes right at the end. So what you do see from this, though, is that the red giant branch is a very short time, right at the end of the evolution. Let's turn the radius off, and maybe we want to plot the logarithm of the luminosity. How about that? You see, that's similar to the radius. Again, around 5 billion years, it's at 0, which means 1 in real numbers. And then it gets brighter and brighter as time goes on. Turn that off. And we can turn temperature on. This shows you the temperature at the surface of the sun as a function of its age. Now, I will raise that to the power of 10. Then we 10 to the power of that, so we get the actual temperature. There we go. If I zoom in on this first part here, we live about here, and you see the temperature's around 5,800 Kelvin, something like that. So that's pretty warm. Now, for those of you doing a project looking at whether the star is too hot or is too luminous to support life on Earth, this is the kind of plot that I think you'll want to be looking at. Now, you don't have to plot versus time. We can turn off the time. We could plot something else. For example, if I want to plot the radius against the temperature, what would I get? I get something like that. I need to zoom out because I've already selected a region. But there we go. There's the temperature as a function of radius for the life of the star. And you can do any of the different variables that are down here. We have central density, central temperature, the maximum temperature in the star. That might not be at the center of the star. That could be somewhere else, and so on. So feel free to have a look down here. See, some of them you'll recognize, some you won't. Ask about the ones you don't. I don't know what all of these mean. That's absolutely fine. Most of them do work, at least. Some are for binaries, such as the J dot here, all of these. These ones might be useful. These are the abundances in the star. For example, XCN is the central abundance of nitrogen. So if I plot that on the y-axis and I turn this one off, let's do it as a function of time. Give it a second to replot. There we go. So there's the central nitrogen abundance of the star. It starts very small. Very quickly it reaches this equilibrium value here, which gradually changes as the center of the star gets hotter, until by the end of hydrogen burning, most of the nitrogen has been made in the core of the star. So you can experiment here with all these different chemicals. You can plot two at the same time if you want. For example, I can plot carbon as well. There we go. So there's the nitrogen being made in the blue, and the carbon is the red. You can also plot those on a log scale, which means you can see the differences more clearly. And you see very quickly the carbon in the core is destroyed in the sun, and it's converted to the nitrogen. And this is the CNO burning that happens in the center of the star. If you don't know what that is, I recommend looking it up and having a little look on it. It's a very interesting nuclear burning cycle. So the burning in the center of the star makes carbon into nitrogen. Now, what if you want to look at snapshots in time, things that happen at certain times? You can look at the internals tab. Now, this is laid out for professionals. So this is not something that is obvious, I think, to most people looking at stars. But remember, I talked about time steps. Now, a real stellar model is not continuous in time. It is done in steps. These are called the models, and they have different model numbers. Now, that's what you're given here as a default. You can see here, you have lots of options if you right click on this. I'm not going to go through all of these today, but what I will do is just turn on Model 2. Okay. Now, what do we want to plot on the x-axis? Well, now we can look at all the internal features in the star. Now, there are two coordinates that are usually used to measure where you are in the star. The obvious one you might think is the distance, which here is r. That's the radius from the radial coordinate from the center of the sphere that makes up the sun. At the center, this will be 0. At the surface, this will be 1 r sun. So we can use that. Let's do that. Select that for our x-axis. What about our y-axis? Well, how about something like the pressure? P of r, the pressure. P as a function of r. And that's what we get. We get the pressure in the star is much higher in the center where r is small. And as you go out, it drops off very quickly. If you right-click on that, you can then say, I'd like to take the logarithm. Now, these numbers are 10 to the power 17, so the logarithm at the top should be around 17. But what you'll notice is that all the small scale stuff becomes visible when I use a log scale. So if we select that, this is a logarithm of the pressure, and you see at the top it's around 17, it's between 16 and 18. And yes, it drops off quickly, but you can still see what's happening in the star, and it's relatively smooth. So the drop-off in temperature is over many orders of magnitude. This is 17 to 16 is 1 order of magnitude, to 14 is 3, down to 12 is about here. That's 5 orders of magnitude. And then you have the surface, where it drops from about 12, 5, over a very small range. So there's a very quick drop in our pressure when we get near the surface. And of course, near the surface of the star is next to the vacuum of space, which has no pressure at all. So this drops all the way down. So that's why it's so low down here. Now you can plot anything you like on here. You can also plot multiple models. So for example, if I choose a model March later on, I don't know, this one, 419, whatever that is, then I right click here and I say copy this row to all rows. You see it fills all the rows with R and the logarithm of the pressure. Now this is what we had before, this is the old pressure, but this is the new pressure at this later model. And you see now the star has expanded greatly, it's up to 2 solar radii, and the central pressure has gone up. From 10 to the 17, 10 to the 20. You can animate these as well. If I choose animate, it should spin. There you go. So you've got animation frames. You can see model 2, then model 419, and so on. You can choose the speed of your animation. In this case, we've only got 2, but it'll flip between them. Of course, the speed goes up to 11, as all good ranges should. There we go. And you can choose many other models here, for example. How is it I do this? You right click on here and you go select from the top, and you can choose every model, every 10th model, every 50th, every 100th, or you can choose percentages of them. So I'm going to choose, let's say, 10% of the models, and you see it's selected for me every 10% chunk. And you see now we have slices going all the way through. It's great. Now, if we turn on the animation, it'll take a few seconds to draw, making the animation frames. You have to be patient here. You can see what's happening inside the star as the models move on in time. You can see the pressure in the center is building up, and you can see the radius of the star increasing. So it's 4 solar radii, 5 solar radii, and so on. And as it becomes a giant, it becomes enormous, 180. Oh, it's very big. Now we can just leave it to zoom through the different images that it's already made. So that's a good way to have an animation should you want it. Now let me pause that. There we go. You can also zoom through, when you've got the animations on, you can change the frame number should you wish to. So you can go through them. Oh, it has to make them again. Sorry about that. That was my fault. It'll teach me to change things. Good thing is we're on a Raspberry Pi 5 here, so it's pretty quick. Oh, 1,000 models. That's why it takes a while. Now we can change the frame number. You see, you can manually switch through from one frame to the other. When you see a frame that you like, maybe one that does something you want, you can right-click on the image. You can copy it to the clipboard. You can save the image. For example, if I click Save Image, I can then choose a file name in here. Usually you want to save in your home directory, and that can save in there. If you copy it to the clipboard, of course, you can then paste it somewhere else if you wish to use some kind of editor. Turn off the animation once we're somewhere, and that's what we like. Other things you can do here, you can use GNU plot options. GNU plot is the plotting tool we use to make all the lines. You can change the colors of the lines. You can put a plot title in here. You can change the fonts. Got lots of lines because I selected a lot of stuff. It shows that it works. And you can set the start labels and stuff like that. Or you can reset everything if you break it. So that's quite handy for customizing your plot. I can show you a couple of other things. We go back to the HR diagram. If I click on Data Viewer, then this is the file where the data is stored. Well, I can click View, which shows me the raw numbers that go into this plot. This is very handy if you want to really explore some detail that's in the data. And you can change the font down here, should you wish to. Or you can save the data. So I can save it to, for example, my home directory into a file, should I wish to. Very handy when you want to then use that data, for example, load it into Python or something like that. There's also the nearest data point tool, which is great. So if I right-click here and go nearest data points, that will give me a list of all the data points in the graph that are the nearest to that one. It gives me not just the age, the mass, the radius, the temperature, all these kind of things. Now remember, we could do this down where we thought the sun was, which was somewhere here. If I go nearest data points, these are the nearest points to there. And you see they have ages around 5 billion years, depends which one. Masses are about 1, which is what you expect. Radius is also about 1, which is what you expect. Temperature, 5,800 or so. Luminosity, that's maybe one and a bit. Oh, that one's just below 1. There's also the, which is the one I want, the point browser. So if I put my mouse near to the curve, if you look in the window that just popped up, you can see lots of information about what this star is doing. So if I go here, for example, I have an age of 6 billion years is the nearest point, radius 1.06, luminosity 1.17, and so on. So I see lots of useful stuff. And as we go up here, you see more information as we go up. So let's go up to here. What's the luminosity now? 35 solar luminosities. Yeah, that's pretty bright. So you wouldn't want to be on holiday near that star because you need a lot of sunblock. So the point browser is quite useful sometimes. You can add data to overlay on top of this. So should you want to put some images on there, for example, observe stars, you could put points on there should you also want to. Now, the final tab that's really useful is the Kippenhahn tab. Now, you may well not know what a Kippenhahn diagram is. A Kippenhahn diagram is one where on the x-axis you normally have time or the model number, which is a non-linear measure of the time. On the y-axis, you normally have the mass coordinate. That's a way of measuring the distance between the center of the star and the surface. So in the center, it's 0, because there's no mass enclosed in the center. Whereas at the surface, it's one solar mass because you've got one solar mass internally. And you can measure surfaces, for example, out to half a solar mass or 0.7 solar masses. Now, the color scale, what we call the Z-axis here, the color scale is then, it represents whatever you're trying to model or whatever you're trying to look at. For example, here, I'll look at the temperature, but actually the logarithm of the temperature. So let's have a look at that. You can change the colors as well, should you wish to. I'm not going to today, but you can change them to play with whatever you like. And I'll hit plot. Now this takes a little while because there's a lot of data sitting in there, which it's trying to do some number crunching with. So I'll come back in a minute when it's finished. So now you see that the Kippenhahn diagram is done. It only took about 20 seconds. It wasn't that long, but it was thousands of models in multiple dimensions, which is why it's not as quick as you might want, but it's still reasonably fast. And what you can see here is the temperature, is the color. So the white at the top here is when the star's lost some mass, but the white at the very top will be 8.5 on log scale, so that's 10 to the power of 8.5. That's nearly 1 billion Kelvin. So the yellow you see down here, that's 10 to the 8, so that's 100 million Kelvin. So again, absolutely amazing that this can get that far. And you can see different time zones going there here. You see the first 200 models. This is what we call the main sequence. This is hydrogen burning in the star. And you see the temperature is not that different throughout most of the star. Even right near the surface, it's not far off 10 to the 7 Kelvin. However, then it switches to a way of burning which is called shell burning. And that's when the star is moving up the giant branch. It's becoming a red giant. And as it does so, the density in the outer parts you see drops. It goes into this pink regime, and then it starts going into this blue regime right at the top here. So the temperatures in the big chunk of the star are now only 10 to the 4 Kelvin or so. Meanwhile, the core has become superheated. And that the reason that the code struggles is because of the temperature difference between these two. And all your nuclear burning is happening in this very thin shell between the two. And you'll learn about that when you go through the course. You have other options here. You could plot the nuclear burning zones by clicking this button. You can plot convective mixing zones by pressing this button. And I'll hit the button to plot that, pause it, and I'll come back. So here you can see we've plotted the nuclear burning and convection zones in the star. The convective zones are, these weird green shaded parts, and the nuclear burning parts are these blue parts down here. So the nuclear burning happens in the core, which is no real surprise. So the star has various mixing zones all the way through it. As time goes on, they change, and that's pretty much what you expect in stars. But this is something you can investigate. So that's the Kippenhahn plot. You can, of course, plot things other than temperature. Let's have a go at something else. I'm going to plot the density. Let's try that one, see how that works. It's still a little slow to load, so I'll pause things. And here's the density, and you see the density is pretty similar to the temperature in terms of it's roughly the same throughout the star on the main sequence, but when you become a red giant, you have this contrast between your extremely dense core, that's 10 to the 6 down here, that's grams per cubic centimeter. Remember, water is 1, so that's, a lot more, 1 million times more than water. But the surface is, that's much less than water, so water is actually somewhere down here. And you see on the main sequence, the density is, 100 or so, but it's not that much higher than water, really. So stars are not super dense when they're burning hydrogen in the core. They do become very, very dense later on. So that's the Kippenhahn tab. That gives you an idea of what that can do. There's a couple of other tabs that might be of interest to you. There's the miscellaneous tab here. It's got a couple of technical settings here. These are called the niceness. Those are used when you run multiple sets of stars at the same time, or you're running this with something else in the background. If you make your code very nice, so you make your evolution niceness up to 19, for example, then your window to the stars will not run and block, for example, your web browser that's running as well. Normally we run that at 0 because, well, that's fine for most of what we do. If you ever have a technical problem, you can click on installation information, And you see in here, you have a lot of technical information telling you about the installation of the code. And you can always copy paste that and send that to me. So if I select it and copy, or select all and copy, for example, you can put it in an email and send it to me if you have problems. The load save tab is currently disabled. I'm sorry about that, but I will fix that in an upcoming version. So as I suggested, money helps. And finally, about gives you a lot of information about the code. And this is a picture of Peter, who is, he's still doing very well. And I recommend befriending him on Facebook because, he goes to a lot of parties and he enjoys it. That just shows the latest version of the code of Window to the Stars code. And this is a useful thing to see because if you have a problem, you can tell me the version and then I can check it against what I've got online. So now if you want to leave, you can right-click the button up here, which is typical for closing an application. There's also this restart button here, which enables you to restart Window to the Stars. Sometimes, there are little bugs in the code and it doesn't quite work as you want. It's not perfect. Nothing is perfect. But you click restart and it should at least restart it for you. So I think that's as much as I can really say as an introduction to how to use Window to the Stars. Now you are only limited by your imagination. Nothing more. So the only thing you need to think about now is, what can I do? Which stars can I run? Do you want to run 10 solar mass, 100 solar mass? Do you want to run very low mass, red dwarf stars? Do you want to check what the nuclear burning temperature is? How long we can live on Earth if the temperature goes up? Things like this. Well, you can do all that with this software. And what's great about it is you can also output the data and you can put it into your own Python scripts, for example, to do any science you want. Very, very powerful, very useful piece of code. So I'm going to leave the introduction there. I hope that was useful to you. The next video, I'll talk a little bit about the layers tool. This is very advanced stuff that not many of you will want, but if you are interested in running more than one star at a time, it might be useful for you. Thanks so much.